All right, so welcome to my series on complex numbers. So the motivation for this series is that when I was getting my physics degree, that I was in an unfortunate situation that I needed to know how to do complex analysis at a high level, and I hadn't taken the class, and it was too late, and because it wasn't a prerequisite for the class that used complex analysis. And so, what I'm planning to do is to make a video series where I go through complex analysis, teach it to myself at the same time that I am explaining the concepts. Just by going page by page through this book called Complex Variables and Applications. All right, so the first chapter is just going over some of the basic definitions and properties of complex numbers. And so, we can define a complex number z to be an ordered pair of numbers, an ordered pair x and y, where we call numbers that are of the form x any value, and for the y value is 0, purely real. And if we have an ordered pair that is x equals 0, but y can be any value, this is a pure imaginary. Okay? And then oftentimes we'll see something like this. The real part of z is equal to x, and the imaginary part of z is equal to y. And so we now want to go over how we can do different type of addition and subtraction of complex numbers and how that works. So let's first start off with some addition. So the summing of complex numbers. Say z1 is equal to x1, y1, and z2 is equal to x2, y2. Then the sum of z1 plus z2 is going to be equal to x1 plus x2, comma, y1 plus y2. And this new z, we can call z3, the x component of z3 would equal to x1 plus x2, and the y component, y3, would equal to y1 plus y2. So maybe writing z equals that is inappropriate. Oops. Okay. And so the next thing we should define is the product of two complex numbers. Okay, so again, z1 is x1 comma y1, and z2 is equal to x2 y2, and we define the product of these two, z1 times z2, as equaling to x1 times x2 minus y1 times y2, comma, and the y component will be equal to y1 x2 plus x1 y2. So all that's equal to z3, so that means x3 is equal to x1 x2 minus y1 y2, and y3 is equal to y1 x2 plus x2, excuse me, it should be x1 y2. Now let's make sure this definition makes some sense. So let's apply this to let's say z1 is equal to 1, 0, and z2 is equal to, let's say, 0, 1. Now, from what we know from regular, ordinary numbers, so all real numbers, is that anything, so this is just the number 1, anything multiplied by 1 equals itself. So we expect z1 times z2 just to equal to z2, since z1 is equal to 1. So let's make sure that happens here. So in actuality, let's use a red pen for actual. Remember, our x3 is going to be equal to x1, x2 minus y1, y2. And in this case, that is equal to x1 is 1, x2 is 0, minus y1 is 0, and y2 is 1. And when we do this multiplication, this equals 0. So our x3 value is equal to 0. Let's see what our y3 value is equal to. y3 is equal to y1 times x2 plus x1 times y2. This is going to be equal to y1 is 0, x2 is 0, x1 is 1, and y2 is 1. This equals to 1. And so we get y3 is equal to 1. And so our z3, which is equal to z1 times z2, is equal to 0, 1, which is equal to z2, which is exactly what we expected. Okay. And so now we're going to introduce an alternate form, which I think most people are actually introduced to complex numbers are probably used to seeing them as. So we can represent the ordered pair x1, y1 to be equal to x plus I, y, where we define I to be equal to the complex number, and we'll just say complex number or unit. And I is defined as I squared is equal to minus 1. It has this following property, extremely important property. But anyways, over here, x and y are real numbers. Real numbers. And so this is the form I think most people are used to seeing complex numbers represented as. And it's just a fancy way of writing this ordered pair. And so just to make sure that with I having this definition, that our rules for multiplication are followed and our rules for addition are also followed. Okay, so for the easiest one to do is addition. So in this case, x1 plus I y1 plus x2 plus I y2, we add these together. Well, this x and this x don't have an I multiplying it, so they don't have a they have a common factor, but they don't have a common factor with the y, so it'd be x1 plus x2 plus, now we can factor out this I from both of the y's. We get I times y1 plus y2, and with this above definition right here, when we convert backwards, we get the definition or the rule for the sums exactly as we had before. So if we scroll back up in our document, we should be able to see that. Right here. It's the exact rule when we work in reverse, which is intuitive and makes sense. So a lot of this initial part of complex analysis is the nitty gritty definition stuff that you probably already know, and that was one of my hardest parts of like continuing the study of complex analysis was actually just reading all the stuff I already knew and try to skip to a point where I didn't know, but there's a fine line where that happens. But anyways, let's make sure that the product rule or the rules for multiplying complex numbers also works out with this form. Again, we're going to have x1 plus I y1 times x2 plus iy2. Now we multiply these two binomials, so distribute the x to both terms, and we're going to get x1, x2 plus I y2 x1. And then when I distribute my y over here to both terms, I'm going to get plus I times y1 x2 plus, now I'm going to multiply the two i's. Remember, I squared is -1, so instead of a plus, this is a minus. And then I will have, the I will go away at that point because it just becomes -1. And I'll be left with y1, y2. So let's group all of our real terms together. So my real stuff is x1, x2, and the minus, let me include that minus, the minus y1 times y2. And then plus our imaginary stuff, which is y2 x1 and y1 x2. So I'm going to factor the I out front again. So I have I times y1 x2 plus y2 x1. Awesome. And so we come back to the same definition for the product of our complex numbers. And so this right here might seem like an obtuse way to define our complex numbers. And in many books, you'll actually see this, for analysis, this part right here, both of these two things, as being your starting point, and you can just derive the rules. But I'm reading this from a math textbook, and why not do one more layer of obscurity by just defining this as an ordered pair? All right, so anyways, I'm done for right now. If you found this helpful, continue to watch these videos. I will continue to make them. Thank you very much.